We're going to walk through an exercise where we evaluate the advantages and disadvantages of feed-forward and cascade control, comparing the two. So we have a situation where there is a, this is a tank. We're trying to control the level in the tank. We have a level transmitter that senses the level, and that information is fed back to a valve. Now the problem is we have a lot of pressure fluctuations on the inlet. They're quite dramatic and frequent, and we want to be able to improve the level control given this disturbance. We also have some outlet flow changes as well. We have some demand fluctuations that happen from time to time. So it's been suggested that we install a flow transmitter somewhere and be able to use that information in our controller, our level controller. So we have a couple different cases that we'll simulate. The first one is to hook up the flow transmitter to the inlet flow and then use the level control to try to reject the inlet pressure disturbance. Now really you might want to use instead a pressure transmitter to be able to measure the inlet pressure, but let's just say for this case we just have a flow transmitter. Okay, that's going to be the first case. The second case is where we're going to do a cascade controller. But in this case we're going to do a flow controller and then have our flow transmitter. Okay, I'll give a little bit more detail about that, and that's going to have a secondary controller that will send a set point to from the level controller. Now the third case is where we'll fit a flow transmitter here to the outlet flow and then feed that information into the level controller. Okay, so that's the third case. So we want to evaluate these three cases, and we have information on the three cases here. We have, as I just mentioned, feed forward, then case B will be cascade, and then case C will be a feed forward control but on the outlet flow. Okay, and we have a little bit of information about the model and the tank. We have a sizable leak in the tank, and that just happens. We are not able to measure that leak, but we know that that is a disturbance as well. We have some initial PI controller tuning. That's already set up for you, so you can just add the feed forward or cascade to that initial PI controller. We also have a step response simulation, so some code that allows you to step things like the disturbances. In this case we have the inlet pressure being stepped up, and then we see the effect on the level. So that causes an increase in inlet flow, as you can see right here, and that causes an increase in the level. And we also have another one, the PI control simulation, and this shows our disturbances right here. We have the inlet pressure disturbances as well as the outlet flow disturbances as well. You can see those with the blue line here, and the inlet pressure is with the red. It's a cyclical kind of sine wave. Okay, so we want to try to reject those disturbances, and a lot of times with feed forward or cascade control we're trying to reject the disturbance before it becomes an error in our process that a feedback controller would eliminate. So we typically always have a feedback controller, and then we add something like a secondary loop, like an inner loop, or we have a feed forward element that we add to it. So let's just go on to, I'm going to go to this other page and just show you some of the simulation results that we have and run a couple of those. First thing we want to do is just characterize our system. We have the valve changes and how that affects the level. So this is used maybe for the tuning of our initial feedback controller. And so here you can see we've just stepped up the valve position from 20 to 30. So that's a plus 10 right there. And then we wanted to calculate the gain. This is our delta U, and that'll be, or delta U is 10, and then delta Y as well. So that's going to be, we have our gain calculation then. We have our change in Y divided by change in U. So that is going to be our KP value, 0.06. And then to come up with a good tuning for the controller, we just take the initial, would be IMC moderate tuning. You just take the inverse of the KP to give us a KC value. And so I just selected about 20 for our KC value. And then we look at the time constant as well for this system. And it looks like it gets about 63% of the way there after about 800 seconds. Okay, so that would be our time constant. And normally with moderate tuning, we would have tau I equals the process time constant would be 800. But I'm going to make that a lot faster. In this case, it's almost a first order system, so we're going to reduce that down to 50 seconds instead. More aggressive tuning. Okay, and that is going to give us a control performance that we see right here. So this is a PI controller. There is our set point right there. We're trying to maintain at a liquid level of 1. And you can see the valve movement from the PI controller. And you can also see these disturbances. So the manager says maybe we want to improve this with this flow transmitter, reduce these variations away from the set point. So let's see what we can do with the first one, which is install this right on the inlet. Okay, so we have our inlet and we're going to install our flow transmitter right here and feed that information into the level controller. Now, if we step the flow, the inlet flow, we're going to get something that looks like this. Okay, we actually step the inlet. I stepped the inlet pressure, but you could also step the inlet flow. And so we have a change here. We have a change of about 2.2 plus 2.2, and this leads to a change in the output. Okay, this is going to be about 0.4, and so our gain between the inlet flow and the level is right here, about 0.2. Okay, so if you want to run that, let me just show you where you can get the code and run this. Okay, here's the PDC website. Go to assignments, and we're going to scroll all the way down to Cascade or Feedforward Control Design. And you'll see the initial code that's right here, the step response code. So just go ahead and grab that, and by default it will do this simulation. We have some other ways to do it as well. You can uncomment for case B, and then you can uncomment for case C. Just comment the case A and case B if you're doing case C. Okay, it'll generate those step responses for you. Okay, let's come back here. Okay, so the thing that we need for the feed-forward control design is we want to get. Okay, here we go. I'm going to write this out in block diagram form just so we can see it a little bit better. We're going to have a set point. That's our level set point. And then we're going to have our, just compare that with our process variable. And that's going to give us an error. And then we're going to feed that into the PID controller, or in this case a PI controller. And we also have a disturbance. In this case, an inlet pressure change is our disturbance. We're going to say it's going to be a flow. We're going to measure the flow. Okay, and then we're going to have that PID controller affect our process. And so this is our process, our tank, and then this is our disturbance model. Okay, and the PID controller is going to adjust the valve, which will adjust the flow. And then we're going to add these two effects together, one of the disturbance and one from the valve change. And so if we want to have something that will reject this disturbance right here, what we'll do is we'll add a feed-forward controller right here. Okay, and add that back in right there. And you know, to derive this, let's say this is our GD and that's our GP, then we're going to have G feed forward is going to be equal to negative G disturbance over G process transfer function. Now a lot of times we just use the steady state, or we use a final value theorem, set S equals 0, to derive the feed-forward gain. So we just set S equal to 0 and of our G feed-forward. Okay, and that's what we typically use if the dynamics of the disturbance and the process are similar. Then those will cancel out anyway, and we'll just be left with a single number, a gain. So for this assignment, let's just do that. Let's just look at the ratio of the gains. And so we can just calculate that. That's just going to be minus G, or K disturbance, all over K process. Those are just going to be the process gain and the disturbance gain. So in this case, we had, this is our KD right there. And this was our KP right up here. So let's just go ahead and divide those two. And in this case, we get a value of -3. Okay, so we're going to use that for our feed-forward controller. Let me just show you how to implement that into the code. And we'll see that we'll get an improvement, a slight improvement. We're rejecting some of the pressure disturbances. As you can see there, it's not fluctuating quite as much, although it's pretty marginal in this case. Let's just go ahead and implement that. If you come back to the course website and just start with the PI control simulation, we're just going to add to that. Okay, so we're going to take this code, and if you do want the solutions, you can look at the show case A source code. I'm just going to walk through it with you. Okay, so here's the original one. I'll just go ahead and edit that. And what we want is to add a feed-forward controller. We're just going to need to add one additional tuning here for the controller. K feed-forward equals -3. Okay, it was -3.03. And then what I need to do is just add in the feed-forward element. And to do that, I'm going to come down to my PID equation, which is right here. The valve equals the starting valve position plus the proportional plus integral, and then I'm going to add the feed forward, and I'll multiply that by the change in inlet flow. Okay, there's my feed forward element that I've just added. Let's go ahead and run this and just see the difference. I already showed that in the plot, but let's just make sure we've got a good controller. So here you can see that just right at the beginning, you know, the feed forward and the feedback controller are kind of fighting each other, and then after it settles out, then you see the the valve is adjusting as that pressure swings up and down. It adjusts to compensate for the pressure swings. Okay, so maybe not the best use of a, I'd maybe suggest a pressure transducer there, but that's the best we can do with a flow transmitter. Okay, so the next case is where we have a cascade controller. So let me come back here and just give a little bit more detail on the cascade controller and how we would tune and set that up. Okay, so in this case, we would, instead of sending the signal straight to the valve, we're going to send that signal instead to a flow controller. And that flow controller is going to get this measurement from the flow transmitter. And the flow controller will be our secondary or inner loop. And the level controller will be our outer loop. So we're just sending now a set point to the flow controller from the level controller instead of writing directly to the valve. So if the inlet pressure changes, the flow controller will take care of that fluctuation and try to maintain at the particular requested set point that came from the level controller. So you're rejecting the disturbance locally, and hopefully you won't see that effect in the final controller. Okay, so in this case I had to make a lot of changes to the code, and so you can see here's the case B source code, and we'll just walk through this a little bit. We have our primary controller right here. Here is our primary level control, and instead of writing to the valve, I just changed that to write to the flow in set point. And I put on anti-reset windup and some other things that are just typical with integral action and controllers. And then that set point comes down to the secondary flow controller. So in this case, we have just another PI controller, but the error is going to be the flow in set point minus the flow in actual. And then we're going to use that to then adjust the valve. So the PI controller is there listed right here in the middle. The valve equals u0, which is the initial valve position, plus P2, which is the proportional part of the PI controller, and then I2, which is the integral part of the controller. Now if the valve saturates, if it gets outside of 0 to 100, then we have to take away that integral accumulation, and that's called anti-reset windup. And then we finally just implement the valve and proceed with the next loop of the simulation. So let's just do one thing here on case B. One of the things you need to do whenever you're tuning a cascade controller is first of all tune the inner loop first. So I'm only going to go to 20 seconds, for example. And let me come down here to my inner loop control. So this has very fast dynamics. I just did a step response on, you can see here I stepped up the valve position, similar to what I did for the process. Okay, this was plus 10 for the valve. And then I saw what the inlet flow did. Okay, so that gave me a gain of about 0.32. So I'd normally take the inverse of that. So that'd be about equal to 3 for my KC value for that controller. So let's just see what happens when I set that equal to 3. Okay, and I'm just going to, I see that the controller is kind of unstable. And so that's not desirable. I only went out to 20 seconds, but you see the flow controller, the thing that you want to look for in particular is this second plot right here, is if the inlet flow is following the set point. Okay, it looks like it isn't. It looks like the oscillations are starting to grow. So I tuned it too aggressively for that sampling time. I could also reduce the integral time, okay, and rerun that, and that would improve it, okay, but still too many oscillations. I'm just going to decrease the gain a little bit. So if I decrease it to 1, okay, and then run it again, then I'll see how well I follow the set point. Okay, so this is okay. It goes up a little bit here and then down, but still it's taking about 20 seconds to make it there. Maybe I can improve the control a little bit by increasing that gain on my secondary flow controller, and so you can see that it's going to improve just a little bit. It's still a little bit of oscillation, but not bad. Okay, so I'm going to go with that, and then I need to tune now my primary controller. So now with my secondary controller in control, I'm going to step the primary controller. So I'm going to give a set point change to the flow controller, and then watch how the level changes. Okay, so now I'm going to tune the outer one. So I've given a set point change to my inner one. It's going to follow that, and then you'll see the level right there. And I've computed a gain. And there's an initial guess for, this would be a good place to start my KC value. There's my KP. And so I'm going to use that one for my controller tuning. Okay, so here it is. I have 6.25, and then I just put in the same integral time constant of 50. Let's just go ahead and run this and see. I haven't changed it yet from 20. Let me change it back up to 900 seconds. I'll go back to 900. I changed that to 20 here. So let me go the full time here and run it one more time. And let's just compare what we have for this one. Now you can see I've rejected a lot of these pressure fluctuations. You can see that the Cascade controller is working to maintain that flow, okay, regardless of the pressure that's happening in the inlet. You can see that's fluctuating up and down. It's kind of inevitable that it drops to, a little bit here because that pressure goes almost to zero. It's really close to zero, so that valve really has to open up to compensate for those pressure fluctuations. Okay, I'll just come back here and show it a little bit more. There's the before. Okay, and here is the after. So you can see it smoothed out that response a lot more. You see kind of this, those pressure fluctuations hitting the level, and so now we've rejected that. We've rejected these large changes in inlet flow. So you can see that those now are much more dampened out right there. Okay, so that has improved it, but we still have some large disturbances that are taking us away from the level control set point, and those look like they correspond to this outlet flow change. And we haven't done anything with that yet. So let's go on to the third case where we might install the flow transmitter. Okay, right here on the outlet. Now in this case we're going to use the same strategy that we did for part A, which was just come up with a feed-forward controller that's going to be the negative of my disturbance gain divided by my process gain. So let's just do a step in my disturbance. Here I just did a +1 in the outlet flow, and then I see my level come down, and there is an approximate gain. So I had a change of about, from 0.8, which is my final, to from about 1. So that's the delta. This is the delta y, and this is the delta u. And so I divide those, and that comes up with negative 0.2. And then my process gain was 0.06. And so I'm just going to implement this one now. So let's go back to our code and just change the controller that we started with. I'll just do this one, and let's just add the feed-forward control just for the outlet flow. Okay, in this case we had negative, and that'll be minus 0.2 divided by 0.06. So that's going to give us a value about 3.3. Okay, and then I'm going to come down here and just change this. This is going to be my flow out instead of my flow in, because I'm looking at changes, I'm measuring the flow out, and then I add in that value. Basically I'm just adding in this term. This is my feed forward part of my PI controller. I'm just adding the feed forward element to it. Let's run this one and see how well it does. Okay, so you can see that when the inlet flow changes, you can see down here in the bottom plot, the blue line, when that increases, immediately the valve opens and increases. And when that decreases, you can see that the valve immediately decreases as well. It doesn't wait for a large error in the level, and it looks like I've improved the level control a little bit. So that completes the assignment, but let's just ask one more question. What about if we just had one more flow transmitter? What could we do with that? Because it looked like case B was pretty good to reject the inlet disturbances, and case C looked pretty good to reject, what was going on with the outlet disturbance. So what could we do if we had just two flow transmitters instead of just one? So let's say we added, in this case, we had our flow controller, and we had one flow transmitter here, Okay, but then we also had another flow transmitter here. So we're going to have two flow transmitters instead of just one, and this will be our feed forward, and this is our cascade control. Okay, cascade and feed forward, and let's just implement both of those. So I'm going to come back into my cascade controller. Okay, this was the case B, and let's just add in the feed forward element for the outlet flow and see how well we can control it with that. Okay, so I had this in here by default. So this is going to say if my outlet flow increases by 1, let's go ahead and increase the inlet flow by 1 as well. I'm just going to put my K feed forward equal to 1. This is going to be a set point to the inlet flow, and that's just going to have, I already had this in there, but I just changed that to 1 instead of 0. And so let's see how well this works. Okay, I'll run it, and there you can see this is much better performance than there was before. Let's just go ahead and analyze this in a little bit more detail. There is the before. Okay, and so you can see that we had a deviation of minus 0.2 on the level, and then afterwards we had a plus deviation of 0.07. So you know, it's a big improvement there. We've reduced some of the fluctuations. Okay, we see that the valve responds very quickly to those inlet pressure disturbances, but we also respond pretty quickly with this flow control set point to these outlet flow disturbances as well. So this is an example of when you can use feed forward and cascade together to try to reject multiple disturbances.